In this talk, I will be using quaternions for Lagrangians in EM and GEM, my unified field theory. First, I need to define what quaternions are, since most of the people in the audience will be unfamiliar with them. Then I will define what Lagrangians are, which are familiar to physicists, although they don't use them every day. Then I will show you the few math tools and tricks we need in order to do the next two steps, which is to go from the Lagrangian to the field equations of EM. In other words, we're going to derive the Maxwell equations, and then the variation on that previous Lagrangian needed in order to derive the field equations for GEM. So what is a quaternion? Well, quaternions are a four-dimensional number useful for events, for potentials, and for four momentums. You can add, subtract, multiply, and divide them like you would any other number. We're most familiar with real numbers, but physicists are certainly familiar with complex numbers which have one real number and one imaginary number. Quaternions have one real number and three imaginary numbers. Now, there's nothing really imaginary about numbers, it's just a bad name that they received historically. So for events, you've got a real number for time and three imaginary numbers for the directions x, y, and z. The difference between the two is that you can point in the direction of x, y, and z, and you can simply record whether something is before or after something else in time, but you can't really point in a direction of time. Potentials also come as a scalar and three potentials that have directions. We can also take derivatives of four potentials, and this represents all possible change. So the four derivative of a four potential ends up with lots of terms. We've got the time derivative of the scalar and the time derivative of the 3-vector A. We also have div, grad, and curl. Now, the way this is normally taught, those are done one at a time because we don't want to scare anybody. Unfortunately, nature keeps all of her books open at all times, and I think this is an accurate representation of change, something with all those parts there together. Now, when I was trying to think about how to handle gravity, I needed something that was very symmetric, and I had to develop what I call the even representation of quaternions. The best thing about this is that everything is positive. So we have this positive divergence of A, and that curl with the box at the end there of that expression actually means that you don't have to remember the right-hand rule, which was useful to try and figure out which one was positive and which one was negative. Everything is positive. So Lagrangians represent all possible ways to trade energy inside a volume. It has units of mass per volume. And what we do to this is we integrate this over space and time, and that's called an action. So if you integrate this over space, then you get the mass. If you integrate this over space and time, you get the mass times time. And what we do with this actually is something called the calculus of variations, another field that is not broadly taught. But the idea is to look for something that we can change, and yet it doesn't change the overall integral. If we have found something like that, then that represents a symmetry, and where there's a symmetry, there's a conserved quantity. And it's this sort of process that allows us to take particular derivatives of the Lagrangian and end up with the field equations. And that's exactly what we're going to do. But first, we need to learn a few tricks. And they're not complicated. Like a Sudoku puzzle, the math rules are simple. They're just used over and over again. So the calculus is simple. The derivative of x squared with respect to x is just 2x. This is probably the first bit of calculus everyone learns, and we need it. But fortunately, it's not that difficult. And the derivative of x times y with respect to x is just y. and I was really surprised that these were the only rules that I needed to know of calculus in order to get to the Maxwell equations from the Lagrangian. Now it does get complicated. It gets complicated because there are 16 x's out there. It's because we're dealing with the 4 derivative of a 4 potential, which makes 16 possibilities. You can see 4 derivatives with respect to phi, with t, x, y, and z, 4 for ax, 4 for ay, 4 for az. So here is the actual animal. This is the Maxwell source equations derived by using quaternion operators. The quaternion operators only play a part in the first 2 lines. And by changing the order in which we put the del with respect to A, we basically kind of flip the sign of B and throwing in a minus sign in there, sort of games we get. We get a minus E minus B times in plus E minus B, and you crank that through and you get a scalar that's E squared minus B squared. Now once we get to that point, the quaternions really don't play a role. So after that point, it's kind of totally standard physics. Just anyway, we've got this Lagrangian of the E and the B field, and we have a lot of terms when we write it out into its components. There are like 18 different partial differential equations there, and we've got 4 terms from the current coupling. And so now what we need to do is to calculate the field equations by taking these 16 sorts of derivatives. And to help you along with that, what I've done in this first one is isolated all the terms that have a phi in it. And you see there's 6 terms that are like that. They all drop into here. Now the E field is minus the time derivative of A minus the gradient of phi, and if you look at that closely, you can see that we've really got the divergence of E. And then we've got a minus rho there. If we throw that on the other side, then we have Gauss's law. So you do a similar process for AX, looking for the 7 places where we see an AX in that expression, and taking these simple derivatives. The outside terms are now a time derivative of EX. The stuff underlined in red, we see some sign flipping there, and we get a sense that that must be some kind of curl thing. And you really need to calculate the curl of A to really understand the details of it. But I've done that enough times to know that the pure terms, which would be the first 2 of these 4 of the red terms, those kind of tell you what it is. If they're minus, then you have just the curl of bx, but since they're plus, that means we have minus the curl of bx. All right, and that basically makes Ampere's law in the x direction. Do a similar exercise for ay. The outside underlined in blue is the time derivative with respect to of ey with respect to time. Sorry, the time derivative of ey, and then we have a minus the curl of by. Similar story for ez, and there is the complete story. Now, I highly recommend that you actually do this calculation by hand and leave the notes on your desk, because if anybody happens to notice them, they will conclude that you are the brightest person they know. And here is our summary statement. We have Gauss's law and we have Ampere's law, and this is known as the Maxwell source equations. So for my GEM proposal, I call it the symmetric field Maxwell source equations. We use these even representation of quaternions in order to get something which is really very similar to what we had before. It's just that we have a couple of sign flips. Specifically, the E field is now small e field is this plus a minus the gradient of phi. And then for the B field, we have this symmetric curl, so that means all those mixed up terms, they all have the same sign. And so again, we get this small e plus b minus e plus b sort of thing. We get a scalar, which is the difference of two squares. We write out all the components. And in this turquoise kind of color, I've noted which signs are different. It's all the pure terms. None of the mixed terms change sign. So what we're going to do here is we're going to do exactly as we did before, and that is take the 16 derivatives with respect to all these possible field things. Here to help you out is the ones that have a phi in them. And we see that the first three guys change their sign, and that's why this is this small e. We've got the divergence of small e. So again, we have another Gaussian-like law. Similar story when we look at the terms with ax, and we get this time derivative of the small e field, and we can tell that this is not the normal kind of E field because those have different signs. And what's nice is the stuff underlined in red, it's all the same sign. It's not as confusing. So this is the symmetric curl story. We've got a similar thing for EY, a similar story for EZ, and then if you want to impress your friends, there's the complete story, and there is our summary statement. Now, I've made a claim that this has to do with gravity. So to do that, what you need to notice is that first line about the Gauss-like law under static conditions. If it's static, then the terms with a dA dt, those will all be 0. And what you end up with is, if you toss the rho on the other side, that the Laplacian of the scalar potential has exactly the same sign as rho. And if that is the case, then there's a theorem of Gauss which shows that like charges attract. Now in EM, in other words the previous set of slides, that the Laplacian of phi had a minus sign. And so it has opposite sign to the rho, and that means that like charges repel, which is a property of EM. Like charges like electric charges do repel. So we get that important feature. But there's an additional bonus here, and that is that with Newton's law of gravity written as a potential, it is what I've derived here. But Newton's law has a problem that time, if things vary in time, it has to happen instantaneously. Well, that's not the case here because we have time-dependent terms, and so this will be polite under a Lorentz transformation. So that's an important qualitative difference. I guess I'll just leave with one other note, and that is the people looking at these things very carefully will notice that I had a very complicated looking current coupling term, and that was the JA term. And the reason that it has to be so complicated relative to what it is in EM theory, which is just JA, is because the spin of the phase has to be just right. It has to be spin 2 to have like charges attract each other. And that took a little bit of investigation, a little bit of creativity, and I have another talk that's devoted just to JA, and believe me, I never thought something so simple would require so much thought, but that's the way this business is. Unified field theory is not a popular subject because if you get one thing wrong, well, why don't we say the critics are rather harsh, as they should be. But if you're concerned about that, the JA term, as I say, look for my other talk on this subject. All right, thank you very much.